Okay, good morning, afternoon, or evening, everybody. Let me just start the timer really quick here. Welcome to the IceFlow and Icepyx Python tools for harmonizing laser altimetry datasets in an open science framework Earth Data webinar. This is your host, Jennifer Brennan. I've got 2 p.m. Eastern Daylight Savings Time, so we're going to go ahead and get started. What I'll do first is just go over a few webinar logistics. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or questions, what I'd like for you to do is enter those into the Q&A pod, and you should see that on the right side of your screen. This works like a chat. Today's webinar is being recorded. The recording will be posted to our online Adobe Connect webinar catalog, as well as to our NASA Earth Data YouTube channel within a few days of completion. Once completed, I will send an email to all registrants and participants with both recording links. As far as timing is concerned, today's webinar will be 1 hour long with 45 minutes allocated to the presentation and live demonstrations and an additional 15 minutes for the question and answer period. What I'd like to do next is pull up today's agenda. Let me just pull that up for all of you. Hopefully everyone can see that. During today's webinar, we will have 3 speakers. Our first speaker is Amy Steiker. Amy is a DAAC Data Services Engineer at the NASA National Snow and Ice Data Center Distributed Active Archive Center, or NSIDC DAAC. She will begin today's webinar with an introduction to NASA's ICESat, IceBridge, and ICESat-2 missions, laser altimetry measurements, and science applications. And then from there, we will transition to our second speaker, Nicholas Kutlinski, a data support specialist also located at NSIDC DAAC. He will provide an introduction to the Icepyx and IceFlow Python-based tools and conduct a live demonstration of IceFlow within the Jupyter Notebook environment. Finally, our last speaker for today is Dr. Jessica Scheik. Dr. Scheik is a research assistant professor at the University of New Hampshire Earth Systems Research Center. She will continue with the live demonstration with a focus on the Icepyx tool. After our speakers have finished with their presentation and live demonstrations, we will move to a final optional set of polling questions, and then generally I will give these questions about 3 to 4 minutes or so, and from there we will move to a Q&A period. During today's Q&A session, we also have 2 additional panelists, Dr. Walter Meyer, who is the Chief Scientist for NSIDC DAAC, and Amy Fitzgerald, who is a Data Support Specialist at NSIDC DAAC. And depending upon the volume of questions that we receive, we will extend the Q&A period an additional 15 minutes from end time for those of you who may wish to stay on the line, but we will have a hard cutoff of 3:15 p.m. Eastern Time. During today's Q&A session, we will try to answer as many questions as possible during the time allotted, but if we don't get to your question, don't worry, our speaker will be able to follow up with you offline after the webinar. With that, it is my pleasure to introduce today's first speaker, Amy Steiker. Amy, I'm just going to pull up the share pod, Nick, so you can share your screen.
All right, great. Thank you, Jennifer. So the focus of today's webinar is on the IceFlow and Icepyx tools, which are aimed at not only harmonizing data from several of NASA's cryospheric-focused missions, but also improving the ways that the ICESat-2 community, in particular, through Icepyx, can discover, visualize, and access those data. And I'd like to say that on behalf of Nick and I and the entire NSIDC DAAC, we are so pleased to have Dr. Jessica Scheik with us here today to share more about the community-developed Icepyx Python library and what has been achieved and is continuing to be developed through their collaborative open science framework. So the outline, Jennifer already provided the agenda today, so just for quick recap with a few more details. So we'll cover a brief introduction to NASA's ICESat, IceBridge, and ICESat-2 missions that these tools are targeting, and the abundance of information and data that have been captured over a long time series. We'll also touch on the challenges that are not necessarily unique to these cryospheric data products in terms of analyzing a record of change over time and across varying instruments and data structures. And then we'll go into detail on what the IceFlow API and associated Jupyter Notebooks provide, as well as the Icepyx Python library's features and capabilities for ICESat-2 data. And we'll provide a live demo of these 2 tools in action, and then we'll just wrap up with a few resources. So first, just a quick introduction to where the data for these NASA missions are provided. The NASA National Snow and Ice Data Center Distributed Active Archive Center, or NSIDC DAAC, we are located in Boulder, Colorado, and we provide access to hundreds of data products in support of cryospheric research, global change detection, and water resource management. So we are one of 12 DAACs as a part of NASA's EOS DIS, or Earth Observing System Data and Information System. And we're also the largest program within the National Snow and Ice Data Center as part of the University of Colorado's Cooperative Institute for Research in Environmental Sciences, or CERES. We have over 700 data products and around 2 petabytes of data, and are continuing to grow daily. So getting into the ice-cubed missions of the NSIDC DAAC. So NASA Earth Science Research has long focused their airborne and satellite lasers on our planet's cryosphere in order to investigate why and how much our cryosphere is changing in a warming climate. So at the NSIDC DAAC, we have 3 laser altimetry missions that, again, make up what we call the ice-cubed mission. These missions span almost 2 decades, and despite differences in spatial extent and focus, provide a wealth of information about the Earth's frozen regions. So starting in 1993, the Airborne Topographic Mapper, or ATM, began collecting high-quality topographic information over the Greenland ice sheet and other locations through 2008. And with the launch of ICESat, in the ICESat GLASS mission in 2003, NASA began collecting polar-specific satellite laser altimetry data using the GLASS LiDAR sensor, which operated through 2010. And then Operation IceBridge flew from 2009 until 2019 and collected laser altimetry data with the ATM instrument to fill the gaps until the launch of ICESat-2, which maybe most of you are most familiar with, in September of 2018. And ICESat-2 continues to collect laser altimetry data with its Atlas sensor. So as I mentioned, all of the data from these missions are stored individually and can be accessed at the NSIDC DAAC. And the abundance of data from these 3 missions, as well as from the earlier pre-IceBridge missions, really presents an opportunity to measure the evolution of ice thickness, mass balance, and other measurements over several decades. However, as I mentioned before, combining data from these missions has presented a challenge to the user community. And so this is where IceFlow gets to work, as Nick will provide more details on in a moment. So to just touch a little bit more on kind of how these missions and data products can vary. So as you can see in this chart, while attempting to tackle similar questions, these missions and their associated products really run the gambit in terms of spatial resolution, temporal resolution, and file formats. So IceBridge, for example, includes multiple different instruments on different aircraft platforms with both ATM and also the ELVIS sensor, which is the land, vegetation, and ice sensor, providing surface height data. And even though these measurements are similar, the variable names can differ, and they do differ across each data set, making it difficult to decipher what variables are appropriate to analyze across a time series. And the ICESat and ICESat-2 satellite missions, they provide global coverage through their, although their accuracy can vary depending on the different surface types, and their coverage and resolution is distinct as well. And cloud cover can provide an additional challenge, which can have a large impact in terms of data gaps. These are just some examples of kind of how these vary. So furthermore, the methods to search, visualize, and access data across these missions can vary, which can add additional steps to an already complex pre-processing workflow needed to harmonize the data. So at the NSIDC DAAC and across NASA EOS DIS, multiple access and visualization methods exist across web-based applications and programmatic means. So feature-rich applications that you could see in the top left quadrant, like NASA's Worldview and Earth Data Search, support a large number of data sets along with common APIs like NASA's CMR or Common Metadata Repository. And the NSIDC DAAC has our own API as well, providing customization options like subsetting and reformatting on many products. But these, however, may not provide functionality that's needed in particular to kind of address the specific needs of our cryospheric communities, So this is where IceBridge Data Portal, you could see in the bottom left, and the advanced Open Altimetry application come in. And Open Altimetry in particular provides on-the-fly visualization of these data values themselves, and also has an underlying API that Icepyx is leveraging in their current development. So this is really where IceFlow and Icepyx become these missing puzzle pieces that are really harnessing many of these shared components in a way that's tailored towards the unique needs of the data sets and our users who are utilizing them. And so just kind of lastly to wrap up my presentation, to kind of give a sense of this data harmonization challenge, you know, the need to combine disparate data is obviously not unique to these IceCube data sets. But when we don't address these challenges, the time that a scientist has to spend to get the data analysis ready really starts to overtake that time that should be spent on the analysis itself. So this is particularly problematic when working with multiple data sets, where, like in this depiction, you kind of end up having to repeat several data discovery, access, and pre-processing steps for each data set, especially when those search, visualization, and access tools vary. So this is where IceFlow comes in, and I'll hand it back over to Nick for more details.
Great. Thank you, Amy. So IceFlow was developed to consolidate all of the data search, access, and formatting steps across missions into a single platform for laser altimetry data users. So what are some of the issues specific to the IceCube mission? So we've seen a little bit in previous slides, but the big ones are that data collected during the Operation IceBridge campaigns are stored in up to 7 different formats, while ICESat and ICESat data were stored in HDF5 format. So this mismatch means that data has traditionally needed to be harmonized or put into similar formats before comparisons could be made. So a further complication is that the coordinate reference systems used to locate measurements have changed over time. To account for changes in the Earth's surface, terrestrial reference frames that relate to latitude and longitude to points on the Earth are updated on a regular basis. So for example, since the launch of ICESat, the International Terrestrial Reference Frame has been updated 3 times. So these changes in geolocation need to be reconciled if meaningful comparisons of these measurements are going to be made. And IceFlow applies the necessary corrections and harmonizes the data for end users so that they can get to work faster. So the IceFlow API allows users to query, subset, and reformat a point cloud database in a format that looks a lot like ICESat data that many of you are maybe familiar with. So this means no more working with multiple formats, no more having to perform your own geophysical corrections, no more having to perform your own spatial and temporal subsetting. The data is now harmonized and ready for time series analysis. So the IceFlow uses a chain of services to provide this harmonized point cloud data to users. So first, the data is queried using the NASA Common Metadata Repository, or CMR. And this is a high-performance, continuously evolving metadata system that catalogs all data and services for NASA's Earth Observing System Data and Information System. And this system makes programmatic search and discovery of the data possible. And then IceFlow is built on a point cloud database of IceBridge, ATM, and ICESat global elevation data converted to the HDF5 format. Finally, Icepyx is used to access and subset ICESat data in HDF5 format through CMR and NSIDC services. And the end result are that data are in a common format with common dictionaries and are ready for further analysis. So with that, I'm going to briefly hand things off to Jessica so she can tell us more about Icepyx.
Thanks, Nick. So in looking at the open polling question, it seems that there are some of you who are familiar with Icepyx as Icepyx, but there are many of you who aren't, who wanted to make sure that we introduce Icepyx. Icepyx is what is used within IceFlow to get the ICESat data, but Icepyx itself is actually both a Python software package as well as an open source community of ICESat data users, developers, and researchers, all who are coming together to practice open science with their ICESat data and ICESat data workflows. So first I'm going to do a little bit of a short introduction to highlight the open science community and collaboration aspects of Icepyx. And then I'll move to talking about the software package itself before we move on to our tutorial, where we're going to showcase both IceFlow as well as some of the unique applications that Icepyx contains relative to the IceFlow tools. So to provide context for the community aspect of Icepyx, I wanted to quickly tell you how Icepyx came about. During the inaugural ICESat Hack Week, which was cryospheric themed, and for those of you unfamiliar with a Hack Week, it's like a software carpentry meets hackathon style workshop geared specifically for scientists to learn technical skills and about software packages related to a given topic, in this case IceSat data, and then apply that tutorial information through small self-selected projects, while the course instructors and other experts are available to help them troubleshoot and answer questions during the project work. So during this inaugural IceSat Hack Week, during the project portion, several of us noticed that many project teams were encountering the same issues and were adapting the tutorial content in very similar ways to reach their specific applications. Each team would work towards its own solution, but there was no easy mechanism to share the solution back to the rest of the group. So the same basic data acquisition problems were solved over and over, rather than being able to move on quickly to answering the science questions that motivated the data acquisition. So Icepyx came about as a way, via a collaboratively developed open source software library, to help minimize that duplicated effort for basic data query acquisition, processing, and ultimately analysis. Since the data user community underpins everything that we do, the Icepyx community also provides scientists and researchers with opportunities to learn the skills needed to participate in collaborative coding and open science without becoming software developers themselves. So you might be wondering what open science is and why you would want to get involved. And I'll make a quick plug for that here. Open science encapsulates the idea that we work openly from satellite design through paper publication to share our data, ideas, processing, analysis, code, and results openly, not just with our lab group or immediate collaborators, and throughout the process, rather than just at the end of a project through a peer-reviewed publication. So why would we want to do that? First and foremost, open science is providing us with more opportunities for feedback and inquiry, which ultimately allows our work to be more successful. So an anecdote that I like to share comes from Fernando Perez, who's the original creator of IPython, and it tells the tale of a joint satellite mission with 2 instruments on board. The team from one instrument was hugely successful. They generated positive publicity, published a lot of peer-reviewed papers, and were able to ask and answer novel questions that led to significant advances in their field. In contrast, the team working with the other instrument on the same satellite struggled to get people to use the data from the instrument, and they ultimately published a few papers using the data. You can probably take a guess as to which group was using an open science approach. Secondly, as Amy mentioned earlier, the data sets that we're working with are becoming increasingly large and complex. And so we need to fundamentally shift how we obtain and work with our data. This is going to include utilizing shared cloud computing resources and accessing data remotely, and building directly on one another's tools and analyses to explore increasingly complex science questions. And I think that Shel Gentman put together a great image to show this, where we're trying to use open science and working on the cloud to free up a lot of time and energy to focus on our science rather than this fundamental data preparation and processing. So with all of that in mind, I'm going to return to Icepyx, which was built using this collaborative open science approach and continually benefits from the addition of new features. So hopefully many of you will be able to provide contributions in the future. So Icepyx is also fundamentally an open source Python package. All of our code is publicly available on GitHub. We have a documentation page that's hosted on Read the Docs. And you can easily install Icepyx via Conda, which is a popular Python package manager, or using pip, which is the Python package index. Once installed, Icepyx provides some easy visualization and programmatic data access in one place. As you can see from the interactive map on the right, which we'll showcase during the tutorial later on, you can, for example, look at your desired spatial extent in the broader context of a map background. We have example workflows that are provided in Jupyter Notebooks, and you can quickly go from 0 to data downloaded in as few as 3 lines of code. However, every step of the process is easily modified to customize your workflow and customize things like those subsetting options that were mentioned earlier. Some recent additions that we've had to the software package include the ability to search for data using orbital parameters or ground tracks rather than not just date and time ranges. And we are currently working on, hopefully in the next week or so, we will have the ability to quickly visualize some of the data before you go ahead and download it so that you can make sure that the data coverage is exactly where you want it. And this behind the scenes uses the Open Altimetry API. And some other things that are in the works are thinking about how to download compatible oceanographic data sets such as Argo and streamlining data read-in into multiple different formats. And so bringing things back to the broader IceFlow and integration with Icepyx, we're going back to this slide as a reminder that Icepyx is part of this larger IceFlow API. And I'm going to turn things back over to Nick, who's going to give you a little bit more information about the IceFlow API.
Great, thanks, Jessica. And so while this broader IceFlow API allows for all data access and formatting options to be implemented in a terminal environment, NSIDC has also built several Jupyter Notebooks for new users and those interested in exploring the data offered before downloading it. And for those unfamiliar, Jupyter Notebooks are open source web applications that allow users to create and share live code, visualizations, and narrative text in a single document. So while the Jupyter project supports a number of programming languages, Python is the most common in the geosciences and the language used in the IceFlow notebooks. A binder link on the NSIDC GitHub page allows the notebooks to be opened in a fully executable environment and ready to be used by anyone. Several Jupyter Notebooks currently allow IceFlow users to learn more about the project, access the data through an interactive map widget or just using the API, and format and visualize the data with pre-configured code. So now we're going to go to our example Jupyter Notebook to do a walkthrough of the data access and visualization capabilities of IceFlow and Icepyx. And you can access the notebook by downloading the NSIDC Data Tutorials repository on the NSIDC GitHub. You can find the link to our GitHub in the links pod of this webinar in this slide that you're looking at right now, and we'll also include this link at the end of the presentation. So I'm going to start at the NSIDC website, nsidc.org, so that I can show you the steps for finding links to access both IceFlow and Icepyx. So first, from the home page, I'm going to choose a data set from the Select a Data Collection button. And I can choose from any of our IceCubed missions, so ICESat, ICESat, or IceBridge, or you could search them using the free text search here. I'm going to go down and I'm going to select ICESat for this example. And so now I'm on the ICESat landing page, and I'm going to choose the Tools tab over here on the left-hand side of the screen. So I'm going to scroll through all the available tools and services for ICESat down to the Icepyx cell right here. And here you can read a short description and find links that will lead you to the Icepyx GitHub repository, and then also this documentation page that I'm going to open up. And this is great for looking up installation information, code examples, API reference and documentation, and a lot of other options for getting involved with the Icepyx community, so contribution guidelines, and a lot more that I would encourage everyone to explore if they're interested in either just using Icepyx or actually getting involved with the community. So I'm going to go back to the ICESat tools page and scroll down, and here we have information about IceFlow on the tools page, and I'm going to open up the GitHub link. So this repository contains Jupyter Notebook tutorials for a variety of data sets and use cases, as you can see here. But for today, we're going to be interested in the IceFlow repository. And I want to introduce us to install IceFlow, we actually need to install the entire NSIDC data tutorials repository. And so the main page's README contains the instructions for running any of the notebooks found here locally, which involves setting up a computing environment to ensure that all the appropriate packages are accessible. We have options for doing this in a binder environment, which does allow users to open a temporary environment directly in the browser without downloading any files or code. And this is a great option for new users or those just curious about looking at IceFlow. And you can find the launch button at the top of the page here. And I'm not going to open that now. You should be aware, though, that if you do use the binder option, any code changes you make or data you download is only temporary and will be lost when you close that window. So we also have options for using Docker or Conda on your local machine. And so Docker, we have set up methods for both Mac and Windows operating systems and Linux. And then we also have a Conda option for setting up the environment locally, and this is the option that we'll be using today. So once you've installed your environment, you can launch a Jupyter Notebook or a Jupyter Lab. And once you've, and I have that open here already. And so once you have that open, you'll see this Jupyter Notebook interface. And when using the IceFlow notebooks, you'll have the option to open several pre-configured notebooks. So the introduction notebook is a comprehensive guide to the missions and data available through IceFlow and contains the map widget, API documentation to get users started with the database, and a lot of other information just to get users familiar with what IceFlow is and does. The rest of the notebooks are shorter, more focused pieces of the IceFlow workflow. So for example, some users may just want to use the map widget, while others may want the flexibility of the API. So you're welcome to just dive right into those. And we also have a visualization notebook with some options for generating ideas for how users can plot and analyze the data. And for this tutorial, we're going to use this time series tutorial notebook that I already have open. I'll minimize this. The objectives of this notebook are to use the IceFlow map widget to select and visualize an area of interest. We're going to access coincident ICESat, IceBridge, and ICESat2 data over the same spatial region. And we're going to use the Icepyx Python library to subset ICESat2 data. And we're going to learn a little bit more about Icepyx capabilities and visualizations. And then we're going to extract common data variables to a GeoPandas data frame. And then we're going to plot and visualize a time series across these missions using all the data from across these missions. So the first thing we need to do to get started is to enter our NASA Earth data credentials. If you don't have these yet, you can go to this link here and you can sign up for a free NASA Earth data login, and then you'll be able to get started. I'm going to run this first cell. And you'll be prompted for your username, password, and email account. and you can set those credentials. And then the following cell will authenticate us and should give us a message letting us know whether we've successfully logged in. So here, because we're logged in, we can move on. So next, we're going to start looking at ways we can search for and access IceFlow data. So first, we have this table with all the available data sets that you can access through IceFlow. So this is really helpful since it can be hard to remember which IceFlow data products go with which mission and sensor. For instance, you can see here that from pre-IceBridge to IceBridge, even though they're different flights, they all use the same sensor, and they all get, and if your search parameters overlap with all these missions, they'll be bundled and returned to you as a single point cloud file, HDF file of all ATM1B data. And that'll be the same for ICESat data. Even if you have multiple granules, it'll be returned to you as a single HDF5 file with all of the granules harmonized within that file. So this is a great resource to kind of know what you're ordering if you're not familiar with all the products. I also wanted to point out that IceFlow does perform geophysical corrections of the point cloud data across missions on the fly based on the user input. These corrections are optional, and in most cases, differences are negligible, but they have been included for researchers interested in making these changes. So these corrections should only be applied by users who are familiar with the procedure behind the corrections. As an example, if you're downloading ICESat data, as well as IceBridge data, you may want to use the ITRF 2014 reference frame so that the IceBridge data matches the reference frame of ICESat2. And based on whatever date of ICESat2 data you're looking for, you would choose an epoch that most closely matches the ICESat2 data date. And you can get more information on these corrections in our corrections notebook that's also included in IceFlow. So now we're going to go and launch the IceFlow Map Widget user interface. I'm going to zoom out a bit so you can see it better. So here you'll see that we have a satellite base map. We have some extra data sets, including IceBridge flight lines and ice velocity layer that might be good for focusing in on an area of interest. We can also use the zoom tool to zoom in, or we can double click. And I'm going to go into the Sarmekkuhalik, or Jakobshavn Glacier, as our area of interest. I'm going to turn these lines off so you can see a little better. And then we also have a polygon, draw polygon tool, and a draw rectangle tool to make our spatial subset search area. And so I'm going to draw that just as an example. This is the general area where we will be looking today. And then down here, we have projection changes that we can make. So I'm going to leave it on north, and this doesn't affect the data in any way. But when you're searching for data, you can choose if you want to look at a global projection, a southern projection if you're looking in Antarctica, or this northern projection that we're using now for Greenland. Then you'll be able to choose one or multiple data sets to download with IceFlow. And right now I'm just going to leave it on IceBridge and IceSat. And then the next section we'll be able to make our geophysical correction selections. So I'm going to use the ITRF 2014. And because I know that there's ICESat2 data that match this date, December of 2018, that will download, I'm going to choose that for my epoch. And then for ICESat2, you have the option to select a single ICESat2 data product for download through Icepyx. And so we have the geolocated photon data, ATL03, ATL06, the land ice height, ATL07, sea ice height, and ATL08, which is the land and vegetation height data sets. So since we're over this glacier, I'm going to choose ATL06. Lastly, we have a date range slider, so you can select your dates of interest. I'm going to leave this alone for now and go start actually looking at the information based on what we've selected on our map. So the map widget doesn't actually print any of the parameters or outputs from these buttons down here. And so what you'll want to do is go to View, Show Log Console to open a log console window, and we can move that down to the bottom so it's a bit out of our way. And we can start using these. So the get raw granule count returns the search, the query information from CMR. So this is giving us an approximate number of granules for each of our data sets and also an approximate download size. So this is without the spatial subsetting of our bounding box applied. These are just granules that touch the bounding box. So your ultimate download will be different than what you see here, but this is kind of a good way to see if you have enough data in your area and if you have data for all the missions that you're interested in. And then next we can print current parameters. So this is the IceFlow API parameter portion. And again, we have start and end date, bounding box. We have all of our data sets included and our geophysical corrections are labeled. So I'm going to close this out. And if you're happy with all your parameters, you can then place your data order, check order status, and download completed orders from the map widget. So you can do the entire data access pipeline from the widget. You'll just need to use that log console. But for this tutorial, I want to also show off the API. So down here, we've entered everything programmatically. And so this is our first order. So for this first order, we're ordering ICESat data and then ICESat2 ATL06 data. We have a slightly smaller search window for this area that we've entered. And then we have a bounding box over that same, a similar spatial subset area. And then we've applied geophysical corrections. And so we can run that cell. And you can see that we have data over that area and we're given approximate number of granules and the size of our download. And then for this example, we'll order IceBridge data, but we have broken it up from our search. So we could have put ATM1B data in the first search, but this is very, very dense point cloud data. So we've broken it up for this tutorial. And so it's a slightly smaller subset, but all the other parameters are the same. And so you can see from CMR that we have quite a bit of data, and it's rather large even for a very, very small subset. So that's something to keep in mind. So next, if we're happy with those parameters, we can go to the cell here and we can place our data order. And this will print out a summary of our data order, including a randomly generated data ID code. We'll have our data set, and then it'll say download pending. And it'll have it for both orders, so the first and second order. Next, we can check the order status, so we can see where we are in the order. So our first order completed pretty fast. So you can see that the ICESat and ICESat2 data is already complete and ready for download. And because that IceBridge data is so large, it is still in progress. So that'll take a minute to get ready for download. So once all of your orders say complete, you can move on to the data download cell. And so here we're going to push download, and we see this bar that shows us the progress. So it went really fast, and then it's still pending, and it should complete fairly soon. If your order isn't ready for download, you won't see anything until it says complete up here. And it's really best practice for each order for all of your data products to say complete before you try this step. You can do it multiple times to get your data, but just for a fluid download experience, it really is better to do that, to wait until everything is said complete. So this first order says complete. So now we can go to our data folder and open that up. And I'm going to choose last modified. I have a lot of files in here. But we can actually see the data that was downloaded. So a second ago and a minute ago, we have our ATL06 HDF5 file and our ICESat HDF file that's been downloaded. You can check this too. Okay, so our IceBridge data is also ready for download and is currently downloading, and that'll be placed in our download folder as well. So after that's done downloading, I'm going to hand it off to Jessica so she can talk a little bit more about how Icepyx works.
Thanks, Nick. Could you make your font a little bigger for me? So behind the scenes, IceFlow is using Icepyx to get the ICESat data, and the primary way that it does this is called through what's called a query object. And so what I want to showcase here is the visualization that you can get of your, if you have a programmatic area of interest that you've entered, such as we did before, how you can view that area using Icepyx. So what I'm doing here is I just go ahead and use the programmatic parameters that we sent to NSIDC and use them to create an Icepyx query object, which is the primary object you would use to get Icepyx data. And then one of the things on that object that you can do is you can visualize the spatial extent. So there's a couple caveats that I want to provide with this. The first one is that currently this feature is not available through the Conda download. In terms of the interactive version, there is a non-interactive version, but for an area as small as the one we're working with here, you would see a global map rather than a, and your bounding box would be basically invisible versus a nice zoomed in map with fun satellite image background. So if you want the most up-to-date features that are happening in Icepyx, you do still currently need to work from the development branch on our GitHub page. That being said, the other caveat for this is that this visualization requires GeoViews. And there, again, are instructions on the documentation for Icepyx that tell you how to install it, because the GeoViews itself has some dependencies that can be tricky to install and have to be done in a certain way. So with those caveats aside, what Nick is showing is the visualization of the spatial extent. And the thing that's really cool about this interactive map, obviously, is that you can now zoom in and out and you can say, ah, that's not actually where I thought it was, or that's, you know, here's the context for the broader region that I'm working in. And it provides you a great way to see exactly where you're getting data. And one of the things that is in the works, hopefully will be released in the next couple of weeks, is the ability to use the Open Altimetry API behind, which will be used behind the scenes. But what it'll allow you to do is to quickly visualize some of the actual data without downloading the entire data set, so that you can see within this region that you're looking at, where does the actual data fall? Where do the satellite tracks fall? And is there actually data in the region, entire region that you're interested in, or did you just get returns because there's a couple points in, you know, the northwest corner of the box? And so now that our data is downloaded, I'm going to turn things back over to Nick to talk about working with the data within IceFlow.
Great. So now we're going to look at a use case for working with the data that we've just downloaded. So the first thing we need to do is load all the necessary packages. And these packages are focused on plotting, data manipulation, and working with tabular data. So they're nothing too fancy here, and you can find out more about these in the introduction notebook and up here in this tutorial. So now we can start importing the data we downloaded and converting it to a GeoPandas data frames using functions that are actually built into IceFlow. So these data frames, I'm doing this for ICESat and ICESat2 granules. And these data frames will have common column names and are geospatially aware, which will make them harmonize with each other and easier to plot. So here I'm plotting the ICESat data frame. And so you can see that we have a time column, latitude and longitude, elevation. This geometry column is this geospatial component. And then we've actually appended this mission column so that we can keep track of individual points based on mission. And you'll see that both of the data sets are the same, which, without IceFlow, this wouldn't be immediately possible. And you can use the same method for IceBridge data, but again, because IceBridge can be so dense, it can be really difficult to work with it in this environment at the scale that we've downloaded it. So for this example, we're actually going to downsample the data for faster plotting and visualization. So in this cell, I'm downsampling the IceBridge data, and I'm just loading in the HDF file, and I'm adding a dictionary that is similar to the other data sets. And so you can see it has similar column names. We have some differences, but we'll take care of that in the next few cells. So then in this cell, we're actually aggregating or decimating the data to make it smaller for our purposes. So we're only keeping every 100th point just to make it a little smaller. And then finally, we're going to convert our downsampled data back into a Pandas geodata frame so that it looks like our other data frames. So here it's slightly different, but you can see we have the same latitude, longitude, elevation, time, mission, and then now we have that critical geometry component that'll let us harmonize the data. So the great thing now is that we can actually plot the data and color it by elevation. So this is all of the data across 3 missions and multiple granules from some of the missions. So using this interactive plot, we can zoom in. And so now we can see all of this data that we've downloaded. So you can see the IceBridge data, this very dense point cloud right here in this polygon. And we have, what's great is that we can see now that we have coincident points over a certain area that have both IceSat, IceSat2, and IceBridge data available to us to do an analysis. So with that, I'm going to hand it back over to Jessica for the rest of the tutorial.
Thanks, Nick. So as Nick indicated, where we have this overlapping data between all 3 missions, we're able to quickly zoom in this case, we're going to just quickly look at a time series of elevation. So what we're doing first is going ahead and just stacking those 3 data frames together so that we don't have to keep repeating our processing 3 times. Then once we have that stacked together, we're zooming in and just taking out the data for a very narrow region near where those 3 data sets all overlap. And that's what we're showing in the cell that he just ran. And you'll notice we also did have to do some filtering of the data because there were a couple of bad values. In this case, a minimum elevation of 0 meters was appropriate, but do be aware that there are valid negative values for elevation in these data sets depending on where you're working. So you'll need to choose an elevation value that's appropriate. And then we can go ahead and do a little bit of data manipulation. In this case, we need to group the data together using a function called group by, which will basically where there are repeated times, we're just going to take the mean elevation at those particular times. And then because we've done the group by operation, we need to turn our time was turned into an index column, so we're going to turn it back into a column so that we can go ahead and plot that time series of data. So Nick will show you that plot. We're not going to get into an analysis of this plot, but this would be, the place that we could now start to do our in-depth analysis of how the elevation in this particular location is changing through time. And with that, we wrap up our notebook demonstration, and I'll turn things back over to Amy for to tell us about some resources.
Great, thank you. Yeah, just wanted to wrap up with this final slide, and then we'll get into our polling questions and Q&A. I believe that Jennifer will also add some of these to the link pod in a moment. So just some resources to recap on IcePyx. Nick has already walked through and demonstrated the IcePyx Read the Docs site. We also have a link to the IcePyx repo on GitHub, and then there is a meetings and discussion page through the Pangeo discourse site that you can also take a look at to get involved in the community. And then with IceFlow, we have the Data Tutorials Notebook, repository of several of our tutorial notebooks provided here, as well as our mission landing pages. And then finally, I'll mention that our excellent user services staff, Nick being one of them, is also happy to help answer any questions. You can email that team at nsidc@nsidc.org. And with that, I'll hand it back over to Jennifer. Thank you.
Okay, thank you very much, Amy. At this point, we will transition to our final optional set of polling questions. We'll give these about 3 minutes or so, and then from there we'll transition to the Q&A. All right, thanks everybody. Okay, we're just going to give this a few more seconds here and then jump directly into the Q&A. After today's webinar is over, I will leave the virtual meeting space open for an additional 10 minutes or so. If you think of additional questions or comments that you'd like forwarded along to our speaker, please feel free to add them during that time period. Really appreciate all of your feedback here. This is incredibly valuable. All right, everybody, I think at this point, let's go ahead and transition to the Q&A. And I just wanted to make a very quick note. The links that were provided on the final slide are available. You should see that on the left side of your screen. There's a pod at the bottom. I think there are 7 links, and I included the contact information for NSIDC DAAC support on the Connect with Us slide, but of course you can download the presentation, which will also have the links and the contact information. You'll find that located in the lower right corner of your screen. With that, let's go ahead and get started with our first question. I'm going to need to just bear with me while I scroll back up to that point. Okay, and so for the additional panelists, you'll need to press *6 to unmute yourselves to answer questions. Walt or Amy Fitzgerald. The first question is there some perspective for integrating the Icepyx to CartoPie library for image visualization and or map generation?
I can try and answer this question. This is Jessica. I'm not intimately familiar with the CartoPie library. It sounds like if they have a way to create an interface, that would certainly be something that could be added as a feature. At the moment, there is not any crossover between CartoPie and Icepyx. So hopefully that answered the question, and if not, I'm happy to elaborate a little bit more.
Okay, thanks so much, Jessica. The next question is there any way to change the vertical reference datum for the photons before placing the order?
Yeah, I can try to address that. I don't believe that we don't have an optional parameter that you can specify if you wanted to, let's say, convert your datum. So that is not an option. I don't know if there's others on the panel, though, that can offer more insight into the datum that is returned with your request, though, through IceFlow.
That's something this is Amy Fitzgerald. I would have to check with our developers on this because I think IceFlow is returning the exact elevation values as the original data files that were ingested into the point cloud. So I don't believe any vertical data. So we don't have an option to change the vertical datum, and so that would have to be legwork on your end in advance. So long story short, IceFlow isn't doing that for you, unfortunately, at least not at this point. And it's not to say that's something we couldn't work on, seeing if we could add in the future.
Okay, thank you, Amy. And I realize, thank you for bringing this to my attention. The full presentation is being uploaded right now, the PDF, into the SharePod. It looks like I had included the outline only, so thanks for bringing that to my attention. The next question is, can you use this package to download ICESat, short name ALY08 vegetation product?
Yeah, this is Nick Kolinsky. So I think that they mean ATL08, the land and vegetation height product. And so IceFlow does provide the user to access ATL08 data but through Icepyx. So that is an option to access.
Okay, thank you, Nick. The next question is, with IceFlow or Icepyx, are you able to download from multi-polygons instead of a single polygon?
I can answer this question. At this point, the answer to that is no. This is Jessica again. Because of a limitation on the NSIDC end, where you can only input a single polygon to the subsetters. However, because it's programmatic access, it would be fairly simple to create a loop in which you are looping through your polygons and just submitting essentially a separate order for each polygon. And one of the reasons that you can't just submit a polygon is because of the way that it's looking for the data. And if you have a multi-polygon that or even a shape file that contains information, perhaps you have a whole bunch of single small polygons in various regions of the world, you know, maybe it's just the tops of the tallest mountains or something. What the high level spatial searches are going to try and basically return you global data and then have to further subset that. Whereas if you only are looking at one polygon at a time, or one, single polygon at a time, it's able to much more quickly and effectively access the data.
Okay, thank you very much, Jessica. I'm just scanning the Q&A pod to determine whether or not there are any additional questions. I don't think I have missed any. If there are any additional questions, please note those in the Q&A pod. We'll give that a minute or two. And if there are not, then what we'll do is we'll log off from the audio component, and I'd like to, we'll thank our speakers, Amy, Nick, and Jessica, and also our Q&A panelists, Walt Meyer and Amy Fitzgerald. But let's give this just a minute here and see if there are additional questions. And again, I have uploaded the presentation in the lower right corner. All right. Well, thank you so much, everybody. We really appreciate your participation this afternoon. And we look forward to seeing you at an upcoming webinar. All right, take care. Goodbye, everybody.
Thanks, Jennifer. Bye.